Okay, let me start. Uh, just once check if the slide is visible. Can you please check? Can you see the slide? I am just sharing the continuity equation part. Is it okay?
Yes, sir.
Yes, sir.
Okay.
Yeah. Yes.
Okay. So we just begun to understand that how the governing equation will work, and continuity equation is this. This is one of the main equation, and then uh, we talk about little bit the Navier-Stokes equation, how it is related to Newton's laws of motion, etc. And finally, we have seen that this is basically a nonlinear equation. Okay, so nonlinear partial derivative differential equation, and it can be formed in different ways, means in different coordinates that we have checked. And then we started discussing that how will be the numerical approach to solve these partial differential equations. And the first step that we discussed, that we need to discretize it. Okay, the differential equation directly cannot be solved in a computer, so it has to be converted to an algebraic form. And for converting a differential equation into an algebraic set of algebraic equation, we need to use some discretization scheme. And we have here finite difference method, then finite volume method. Why the pen is not writing? Okay, so this is finite difference method. God, what's the problem? The pen is not writing. Then I told you, it's irritating. What's the problem? Where is the mouse? Okay. So finite difference method, then finite volume method, and finite element method. And after you getting the algebraic set of equations, we need to either adopt Gauss elimination or Thomas algorithm or Gauss Seidel. There are so many methods. And then we need to apply the boundary conditions, and we need to be careful about the numerical errors. So these 4 steps are there. Now, as I told you, that if I start working with the Navier-Stokes equation, it will be very difficult for you to understand. Okay, because that's a big equation. So we will try to understand the strategy with a very simple differential equation. So if you can understand it, then that can be scaled up to the Navier-Stokes equation. That will not be a problem. So let us go to next one. So here we will discuss little bit about the boundary conditions. Boundary conditions can take place, can be defined in 2 ways, mainly 2 ways. One is called Dirichlet boundary condition. Okay, so Dirichlet boundary condition is given by this type of equation. Sorry, extremely sorry, it is causing some problem. So Dirichlet boundary condition is given by, let me drop this, this is not going to work, the pen pad is not working, let me use the laptop first. Just 1 minute. It's causing some problem. Okay. Let me go to the traditional mode. Okay. I'll before going to the details of solving differential equation, let me show you the different types of boundary conditions. So one type of boundary condition is called Dirichlet boundary condition, which is like this. If you have a domain like this, let's say 0 to L, this is a domain. So this is 0 is a 1 point and L is 1 point.
Sir,
So
your slide isn't visible.
we're not visible. Just a
Yes.
minute. Let's go.
Yes, sir.
Now check.
Yes, sir.
Yes.
Now it is visible.
Okay, so I am discussing the different type of boundary condition. One is called Dirichlet boundary condition, where what happens if the boundary of the domain, that means at L equal to 0 or L equal to L, your values will be given precisely. For example, at at this initial point, your let's say it is temperature, so it is T equals to T1 will be given specifically, or T equal to some function of T will be precisely mentioned. Similarly, at this right hand boundary, your T2, T equals to T2. So the specific value, so T1, T2 may be any value, 100, 200, anything. So if the value is directly given, then that is called Dirichlet boundary conditions. Okay. So if it is very easy that if this boundary condition is given. Another type of boundary condition where not specific values are not given directly. Okay, rather it is given in the gradient form. Gradient form means your dt dx will be equal to 0. Let's say at x equal to L, means at this right hand side, your instead of specifying the temperature uh, value, it is showing that there is no more temperature change, dt dx equal to 0, or dp dx equal to 0, pressure change. Generally in flow solution it is happened. Let's say if you have a pipe like this, and if your flow enters in this, then we call that initial at the inlet boundary condition will be having some velocity, say let's say v equal to 100 meter per second, and at the outlet we generally do not know that what is the value of velocity, because that is not required. We just want that there is no more pressure gradient. Okay, it's a free surface, just what fluid is going out and falling into the in the environment. So here this boundary condition is called dp dx equal to 0. That means pressure gradient is no more existing. So it's a free surface, it is just fluid is moving out. So this type of boundary condition is called Neumann boundary condition, where boundary condition is given in terms of a derivative. Okay, not precisely mentioned. And if there is a mixture of these Dirichlet and Neumann, then that kind of boundary condition is called Cauchy's conditions, like this, that left hand side it is given Dirichlet, right hand side it is a boundary, it is known as a Neumann boundary condition or Neumann boundary condition. So these two type of boundary conditions are generally encountered in most of the applications. So with this knowledge, now we will move towards the finite difference method. Okay, so I told you that what is finite difference method? Finite difference method is an approach which will help you to convert the differential equation to an algebraic equation. Okay, so there are so many methods. I told you, either finite difference method, finite volume method, finite element method. So many varieties are there. Very simple to understand is the finite difference method. That's why let us discuss it at the beginning. Okay, so I will not go to the direct detail of it, but very briefly I will try to make you understand that what do you mean by it. Look, the basic objective is to convert the differential term to an algebraic term, right? And that's why in this finite difference method we use some quotient, finite difference quotient. Quotient means what? That if you have a dy dx term, this y dot x means this is dy dx. This can be written as, can be approximated as y equal to x plus h minus yx by h or delta h, whatever, where h is a very small size, small incremental value along the x direction, because this is dy dx, x is independent and y is dependent variable. So dy dx, so in terms of there is a h equal to a delta x value. So this is a very small increment y equal at x plus h minus yx by delta h. So this now, so this is an assumption, this is called the finite difference quotient. So let me read out the lines first. That finite difference methods are techniques to find numerically approximate solution to ordinary differential equations and partial differential equations. Here we are dealing with partial differential equation. They are based on the idea to replace the ordinary or partial derivatives with a finite difference quotient, for example this one. Now the various methods differ by the choice of finite difference used in the approximations. Now whether this is x plus h minus yx, or it can be considered yx minus h plus yx by h, so that all can be done. So based on that, this kind of uh, um this kind of quotient can be derived. For example, forward difference, this is forward difference, where dy dt, here instead of x it is taken t, anyway it is same thing, dy dt we can be written as yt plus delta t minus yt by delta t up to this one. Okay, this is plus order of delta t terms. Basically this will come from the Taylor series expansion. So you might have read in your mathematics courses Taylor series. Taylor series is basically applied to a continuous function. So what if there is any continuous function, you can write fx plus h will be equal to fx plus f dot x plus 1 by 2 factorial f double dot x, like that. So that is a series. Okay, so you can approximate any continuous function in the form of a Taylor series. Now in the Taylor series, if you see, you will see that left hand side is a algebraic term and right hand side contains some differential term. So we are basically using the concept of Taylor series and truncating it after some order, some terms. So after first order derivative, we are basically truncating this part. So this is and due to this truncation, because you are not considering the entire Taylor series, some error will be introduced which is known as truncation error. Okay, now truncation error will be of the order of delta t here in this called forward difference. Now why forward difference? Because you are taking a forward point at t plus delta t minus yt by delta t to approximate this. Similarly, backward difference can be taken where dy dt, same dy dt can be defined as yt minus y minus t delta t. Here there will be a t, so y into t minus delta t by delta t. The order will be of same thing, same delta t order, this truncated form. Now there is another thing which is called central difference. So if you expand the Taylor series both in positive and negative direction and then you take the sum, you will get dy dt of t will be equal to y t plus delta t y t minus delta t by 2 delta t into delta t square. Now this has some advantage because here the truncation error will be of the order of delta t square. Now if delta t is very small, then the delta t square will be much smaller. So central difference is more accurate. So all these things, in all these are different scheme: forward difference, second backward difference, central difference. These are different scheme where we are expressing the left hand side is differential thing, right hand side is an algebraic part, right? So this conversion we are doing here. Now you can choose any one based on the situation. However, if there is any choice is given, we should always prefer for central difference because it is one order more accurate. Now those who are not cannot recall Taylor series etc., you can revisit it later, but for the time being just remember that this dy dt can be replaced by this kind of algebraic quotient, okay, in any equation. Similarly, this is first order derivative, second order derivative also can be written in this way, okay, and all these can be derived nicely from the Taylor series. So you just for the time being accept it without remembering the derivation etc. That if there is any differential equation means what? It will be having either dy dx, dy dt, this kind of terms, or d2y dx square. So all these things can be replaced by these kind of coefficients. So if any equation you replace the dy dt etc. with these right hand side terms, then you can convert a differential equation to an algebraic equation, right? So that is our objective of discretization. Now up to this I am telling, I don't know, things will be very clear if I take an example. Okay, take a small example and show you that how this method can be applied. Okay, then things will be more clear. So let us take an example problem with finite difference method. So I will take this one dimensional heat conduction equation. I generally do it in my class, so it is a handwritten. I hope it is clear to you. Let us take this example. Let me read it out. It is an one dimensional heat conduction equation. That means what? Heat is flowing, let's say for example through a rod. Okay, so in a rod you are considering one rod, one end of the rod you are heating and other end you are keeping it at a cold temperature. Okay, now you like to see the temperature distribution in the rod. Very simple problem where conduction is taking place in only one direction. Okay, and there is no convection part. Okay, so to simplify the situation, so the problem may come up to us like in this manner, that consider 1D steady state conduction without heat generation. That means there is no generation term. You are just putting one end at let's say 100-degree water and other end at the ice of a rod. Now there will be temperature change, so steady state will be reached. So we like to know the steady state temperature distribution in the rod at each point. Okay, so how to find it out? So that is the objective. And it states that there is no heat generation, means no generation term is there in a rectangular slab or rod, whatever you consider. The temperature of the left hand side of the slab is 100 degrees centigrade and right hand side is 200 degrees centigrade. So one end is at 100 degrees centigrade and other end is 200 degrees centigrade. The length of the slab is 10 centimeter and the thermal conductivity of the slab is 120 watt per centimeter Kelvin. Then it is told here that make 9 uniform divisions. So this is in CFD problem, this is not precisely given. Generally you have to take a number of you have to take the number of grids or number of points, but in this problem it is given that you take 9 interval and the governing equation is this one. This is k into delta 2t delta x square equal to 0. So T is temperature, X is the length and K is thermal conductivity. So as you know, so this is the simple equation, most simple second order differential equation. So I like to solve it with finite difference method to show you the applicability of the process that I am describing right now. If you can understand this, the same thing will be scaled up for Navier-Stokes equation. So let us see first. This is the slab, I have one dimensional, that's why I am just drawing a line, and I can 9 interval means 1 2 3 4 5. So these many points are there, I equal to 1 2 3 4 if you mark. So from initial to end it will be 10th point. So at one point it is 100 degree, boundary condition is given. This is Dirichlet boundary condition. Note that precisely 100 degree is given, and this is also Dirichlet boundary condition, 200 degree is given. Now your equation is this. Okay, kt d2t dx square. So what I told you, the first step will be to convert the differential equation to an algebraic equation with the help of the quotient for finite difference quotient. Okay, so the whatever the quotient I was talking about, this one. So here it is second order. So we will consider this formula d2y. Here t is given, but in our given problem it is x square. So your t will be replaced by x. So this will be the form. Okay, so this part I can write in the place of that second order differential term. So that is what we are doing. You will see k into t I plus 1. I plus 1 means that x plus h that is written there, minus 2 ti minus 2 I minus 1. Now the I is indicating the indices of all these points, I equal to 1 2 3 4 to 10. So in term at any point, arbitrary point I can write it in terms of this ti plus 1 minus 2 ti plus 2 ti minus 1 by delta x square will be equal to 0. So this I am getting from that central difference coefficient. That is why it is written CDS, central difference scheme, it is written. Now if you rewrite it little bit, because delta x square and k will be cancelling out, those are non-zero quantities, so you can neglect them. So your point is coming, you just write it minus ti, I am just changing the sign, minus ti minus 1 plus 2 ti minus ti plus 1 will be equal to 0. Okay, so this is the equation that now we need to solve. Okay, so let me go to the next page. So this is the equation, final equation. Now I will write it for all the points, because the finite the differential equation I like to solve in this geometrical domain. Okay, so this is a simple CFD problem basically. So what I am doing, I am defining the geometry, I am discretizing it into a number of points. Okay, so this is called geometric equation and meshing. Then you are setting the differential equation. Remember the steps of CFD. First step is to finalize the geometry, then discretize it. So that's what we have done here. Then we have fixed the governing equation, then the equation we have discretized. Okay, and now I will write this for all the points that is available for I equal to 1 to 10. So for node 2, so if I write it for node 2, that is I equal to 2, uh, 2 t I minus 1 means that will be t1 plus 2t2 minus t3. Then this t1 is basically 100 degree centigrade, that is given, right? This t1 is 100 degree centigrade, that is defined here. So if I write I equal to for 2, so this 100 we can put it here. So that's why we are writing it minus 100 plus 2t minus t3 will be equal to 0. So if you take that minus 100 to right hand side, this will be your first equation. So you see that at I equal to t, if I write the differential equation, now it is a algebraic equation. Simple 2t minus t3 will be equal to 100. Right? Now for I equal to 3, I equal to 4, if I keep on writing, then these kind of equations you will get. For I equal to 3, you will get t2 minus t2 plus 2 3 minus t4 will be 0, I equal to 4, these things, and it will be a series of equation. Then I equal to 9, you will get t8 minus 2 t9, and then t10. And the t10 value is given because t10 is the other boundary, that is 200 degree centigrade, that is defined here. So this is the value. Now all these equations, you see that in all these equations there is only 3 terms. Okay, so if you can write them in the form of matrix Ax equal to b, so you will see that A matrix will be a tridiagonal matrix. Okay, so this is what, this is a set of linear algebraic equation. Now you can apply either Gauss elimination or Thomas algorithm or Gauss-Seidel method to solve it, so that you will get all these t2 t3, these unknown variables, and that means what, you can find out the temperature at each point. Okay, so this is the most simple CFD problem with a heat conduction. Okay, where one rod is kept, rod is taken and the two end is kept at 2 different temperature, and I am trying to calculate the temperature at all the intermediate points. Now if you like to get at these intermediate points, you refine the mesh. So instead of 10 points, you take 100 points, then you can get closer value, so that you can get the entire temperature distribution in this domain. Okay, so this is the application of finite difference method to a CFD problem. Okay, so is it clear? Just let me ask you at this point of time, is it okay? Yes or no?
Yes, sir.
Okay, if any questions you can ask. Okay, now let us take one more to emphasize it a little bit more. So this this is basically a similar type of problem where we have a fin. Okay, so you know that in heat exchanger surface sometimes fins are employed to enhance the surface area for convection or conduction. Okay, so here is a heat transfer surface which is at 320 degree centigrade, which is wall actually, and with each a fin is attached, and this fin length is 0.5 meter. Okay, and the surrounding temperature is 20 degree centigrade, and here it is 320 degree centigrade. Thermal conductivity is given 50 watt per meter Kelvin. Okay, now the question is that you need to find out the temperature distribution. Okay, so boundary condition is given that at x equal to 0.5, the boundary condition is like this: d theta dx plus h by k into theta will be equal to 0. So the governing differential equation, this is also a heat transfer problem. The temperature of the wall is 320 degree centigrade, and the temperature of the fin at x equal to 0.0125, 025, and these values using finite difference technique at these 4 points you need to find out. So you need to find out the temperature at here, and this 4th point. Okay, and the convective heat transfer coefficient from the rod to the surrounding is 100 watt per meter square, because this is a here convection is coming into picture. Okay, so convective heat transfer coefficient is given by 100 watt per meter Kelvin, which is defined by this H. And at left hand side there is Dirichlet boundary condition, and the right hand side you are given this is called Robinson type of boundary conditions, where this d theta dx plus h by k theta equal to 0. So it is in the form of a equation. This is given. Now how to solve it? The question is how to solve it. So here also start from the, you first find out the governing equation. This is the governing equation. You simplify it by, if there is possibility of simplifications. A number of variable can be sometimes clubbed into one thing, like this m. Here it is m is written hp by ka, p is perimeter, ka, etc. So this term is written as m to simplify the problem. So the equation is becoming minus d2 theta by dx square will be plus m square theta. Theta is denoting the temperature, means it is defined by T minus T surroundings. Okay, it is the difference between the temperature of the rod and the surroundings. So that difference in that theta form, the equation is given. Okay, instead of direct temperature, it is given in the form of this temperature difference. Now again, this is a second order differential equation. So you use central difference scheme, that formula, to transform this differential term into this one. Okay, so that is how you are converting it into an algebraic one. Now if you simplify it, it will give you an expression like this. Okay, so this type of expression you will get. Now again, this 2 plus m delta x square can be a constant term. You can term it as a d. This kind of clubbing of several variables into one parameter is a common practice in CFD, so that your equation will be simplified.
Sir,
So yes.
please share your screen.
Oh, slide is not visible.
No,
It is
sir.
showing
No,
visible.
sir.
Yes, sir. Now.
Visible. Okay. This was visible, na? Is the equation the first problem? Was it visible?
Yes, sir. Yes, sir.
Okay.
Up to
Okay.
this.
Up to this it is visible. So if I again discretize it, then using central difference scheme and we little bit of algebraic simplification, if we do by defining a new variable d equal to this, or 2 plus m delta x square. Delta x is the grid spacings. Okay, so that then you will get final equation. You are getting this one. So this is also a linear algebraic equations, as you can see. Now here we see that in this problem we have 4 points: 0, 1, 2, 3, 4. Okay, 1, 2, 3, 3, 4. Basically, these 0 and 4 are boundary condition. 1, 2, 3, 3 equations will be there. Now, if I write it for I equal to 1, then this I equal to 1, then we can write theta 0 because I minus 1, that is theta 0, and theta 0 is given 300 degree centigrade, I think 300 or 320 degree centigrade. So it will be 320, and then minus d theta 1 minus theta 2. So you see, so this will be equation number 1. Similarly, for I equal to 2, that means the second point if you write, then you will get another equation. So another 3, then another equation, and 4 another equation. So in the fourth equation you are getting this theta 5 term, which is beyond this boundary. Okay, now you need to consider an imaginary point here in order to get this Neumann type of boundary conditions. Okay, so this again, this boundary condition needs to be uh, simplified. Simplified means it has to be discretized. Okay, because differential equation is not permitted. So this hypothetical theta 5 node you need to consider, and the boundary condition at L equal to x equal to L, that means node 4, we have, this is the boundary condition. Now if you use finite difference, then you can get theta 5 minus theta 3 by 2 delta x by central difference scheme. H by k into theta 4 will be equal to 0, and from here theta 5 can be expressed as this one, theta 3 equal to this one, in terms of theta 3 and theta 4. Now if you replace this theta 5 in equation 5 means this one, because this theta 5 is not known, this is an outside the domain. So we convert this theta 5 in terms of expressing this theta 5 in terms of theta 3 and theta 4, and then we are substituting theta 5, this 5 in that equation 4, so that this is the final form of the equation 4. So now there is no hypothetical point, we have simplified it. So the 4 final equations are coming out like this. Okay, so this is what, this is a set of algebraic equations. So again, you try to now this value of d etc. can be calculated from the given values of conductivity geometrical parameters, and if you apply any method like Thomas algorithm or Gauss elimination, like this, so this is the set of equation. Now you see this is Ax equal to B form. Okay, and this A is tridiagonal matrix, so it is better to use a Thomas algorithm code to get the value. So you will get the value theta 1 is 248, theta 2 213, theta 3 191, theta 4 181. So that was our objective in the problem, that in this field I needed to know the temperature distribution. Okay, so all the points I can get the values. Now since this is a manual problem, I have taken only 4 things, but realistic CFD calculations, this mesh will be very fine. Okay, not so crude. So maybe in this 0.05 meter domain, I can consider 1000 grids. So 1000 grid means you have a set of linear algebraic equation, 1000 equation with 1000 unknown variables. So this matrix will be 1000 by 1000 order basically. Okay, so that kind of big matrix you have to solve. Okay, so that's why computer is needed. You cannot solve manually a matrix, means Ax equal to B, if there is a set of equation and A is containing 100 by 100 elements, then it is not possible to manually calculate. So that is the role of the solver, that how to solve the problem. Okay, so this is in a very simplified way the application of finite difference method for CFD application, taking the example of heat transfer. So here no fluid flow is taking place, because the momentum equation will come into picture, means if Navier-Stokes will come, it will be very complicated. We will discuss that in the next weekend, in the final 2 lectures. Okay, but for the initial thing, I am just giving these simple 2 examples to show you the approach, that how a differential equation can be solved numerically with the help of finite difference method. Okay, so if you have understood this approach up to this point, then one step is over. At least the beginning part you is done. Okay, now we'll let us know, it is too much mathematics so far, so I will not go into any of the mathematical part today anymore, because this is, you need to first digest this part. Now I will go to the ANSYS Fluent part. Okay, so ANSYS Fluent, I asked you to install the student versions. Maybe some of you have tried it. Okay, I tried to install it. Now first I will take a small example to show in a very brief manner the different steps for setting up a problem in ANSYS Fluent. Then that will end the end this lecture. That is actually we supposed to complete in the morning. Then after that, after a 2-minute break, we will start the next session, where I will go through a case in ANSYS Fluent in details. Okay, so how to set up the problem. Okay, so let us see right now this simple example problem in ANSYS Fluent, how it can be given. By the way, how many of you have tried to install it? Anyone tried it?
Yes, I tried, but
Working?
I can't understand how to work.
Okay, okay. If you have understood, then let us, after today's classes, you can take a try with this example problem. Okay, I will show you two cases. I will I will clarify. First, let us take an example of water flow through a rectangular channel of 1 meter length and 10 centimeter width with an initial velocity of 0.01 meter per second. Okay, an objective is to find out the velocity profile in this domain. Am I online?
Yes, sir.
No, yes, sir.
Okay, okay. So let's say this is a very simple geometry. We have a rectangular domain. I am assuming water is entering from this left hand side and exiting from right hand side, and 1 meter is the flow path length, and your initial condition is 0.01 meter per second, boundary condition at the left hand side. Okay, and anything there is nothing is given at the outside, because that means we will assume that there is no specific value. It is just Neumann type of boundary condition, dp dx equal to 0 in the right hand side. If anything is not given, means I can assume there that part. Okay, so here it is Neumann boundary condition, it is Dirichlet boundary condition. Now what is our objective of CFD study? That we like to know that what will be the velocity distribution in this domain, means where velocity will be high, where low, if there is any vortex formation, if there is any dead space. So that will be clear if I can get the velocity contour. Contour means at each point the velocity value is, if it is given and if you plot it, then you will get a contour profile. That can give us lot of information. Okay, so let us see how uh, this can be designed in ANSYS Fluent. So you have to start with ANSYS Fluent. If you can install it, you just click on that button and you have to open a workbench first. Okay, so you will see that I think if you can see that this is workbench. Okay, so uh, if you install it in your system, if you go to the what that called in left hand corner, the options button, if you go and if you go to the ANSYS window, then you will see there are so many options and you can get the workbench option. Let me see if I can show it in my computer. This work. So you should go to this button. Then if you ANSYS, okay, so ANSYS, the moment you will type, there are so many options will come. Okay, but you have to see where ANSYS Fluent is. Viewer configuration. No, I think it is not work. It will not work. Licensing settings. There are so many. Help conference. Let me see if it works. No, my license has expired. Okay, so I tried to install it, but it is given for license is given for 1 or 2 years, so it is expired already. So anyway, so if you go from that window, then click it, then you will get an option called workbench. Okay, so you click on that workbench part, which is shown here. This workbench you open. Okay, the moment you will open the workbench, this kind of window will be visible to you, and you will see that there is an option called ANSYS Fluent. here fluid flow fluent, this part. Okay, this here fluid flow fluent. Actually this left hand color, left hand part, left hand window will show you several options, because ANSYS is a bunch of several codes. Okay, fluent was earlier is a different separate independent company. Okay, later on ANSYS took over it and it became a module of ANSYS. So these are different modules. You will see a lot of modules are there, and these all these have some special feature for particular set of problems. So you go to the fluid flow in bracket fluent options. If you click that, this window will come, fluid flow fluent. Okay, so this window will be visible to you. Now look carefully what is there. First there is geometry. Okay, then there is mesh, then there is setup, then solution, then results. So these are the steps. So if you recall, in the first class I told you that what are the steps of CFD, that first you need to specify the geometry. So as in that example problem I was showing that this is a rod or this is a fin. Okay, so that's geometry you need to draw. Okay, so that is the geometry construction part. Now if that is done, you go to the next stage, that is meshing part. So you need to mesh it. So mesh means in that one dimensional heat conduction problem I have just divided it into 10 points like that. So in this kind of fin, if it is 2D, you can take XY lines so that the entire domain can be divided into a number of points. That is called meshing or grid generation. Okay, second step. Then called setup. So setup comes means that in the third step, setup means you need to finalize the equation, that what equation it is. It is steady state equation, unsteady equation, 2D, 3D, that everything you have to define. Then comes the solution part. Then you have to set the solution, because this you are solving Navier-Stokes equation. So number of algorithms are there for pressure velocity coupling or the method of discretization. Okay, there are so many things will be available, so that you need to set up. After that you need to run it, and after running you will get the results and you can do the post processing. Okay, so this window basically is showing the different steps of the CFD. So first is what? First you have to go to the geometry part, or geometry construction part. So what is the geometry here? So as we have defined here that this is our geometry. A rectangular box is there of 1 meter length and fluid is flowing from this direction and going out from this direction. So this rectangular geometry we have to draw, right? So the next step, if you click on this geometry bar, this window will be open to you. Okay, so this geometry construction, there are right now two options. One is called what the, I forgot the name. Another one is called space claim. Okay, so these two options are there for geometry construction. Basically these two are two different CAD interface. If some of you have little bit of CAD knowledge, that it will help you to generate, it will be nothing for them. But those who are new to it, so you need to know, you need to practice some tutorial videos to understand that how geometry can be constructed. So this window will appear. So in the next class, next lecture, I will show you step by step that how this can be done. So you see that there are so many options: XY plane, XZ plane, YZ plane. Then you can set up the dimensions here. Okay, then you can age. So by that way you can create it. You can select a rectangle box and put it here. You can set the dimension and you can set the plane, which plane you like to do it. Then you have to create the surface out of it. Detail step I will be coming into the next example. And then you mesh it. This is the meshing step. After that meshing, you need to go to the specification of the model. That means governing equations and material you have to specify here. So governing equation means it is either multi-phase or single phase. Energy equations are there or not. Viscous force will be considered or not. So there are many options will be available that you have to specify here. Then you have to specify the boundary condition. That means what will be the inlet boundary condition, inlet velocity that is defined here. What will be the boundary condition at the wall. Okay, so at the wall we generally consider no slip boundary conditions, etc. So uh, uh, so this is how the steps will go on. Just 1 minute, let me take a call. আমি একটা ক্লাস নিচ্ছি পরে। Okay, so this is so here boundary condition you have to specify. After that you need to fix the algorithm. Okay, so there are so many algorithms. Now what this algorithm means, this simple, least square, so these you can understand at the very end of this workshop. Okay, so these are the most tricky part of CFD. Okay, so I will cover it probably in the last 2 classes. Okay, so then only you can clearly understand. I am just showing you that how step by step you can move onward. And this is the specification of the solution algorithm and start solving. So you finalize it and solve. The moment it will start solving, you will see that some numbers will keep on appearing here. So that indicates that solutions are going on. And then finally when results will come out, you can get like this. So you see that this is a contour. This red values indicates high value. Okay, and this blue is basically 0. Blue means blue to red is gradually increasing. So if you zoom it, you will see that there will be blue at the walls, since this is no slip boundary condition, and maximum velocity you will get at the center line, and that is expected. If you have read fluid mechanics, you will see that in the parabolic profile is obtained. If it is a laminar flow, then at the center line you will get the maximum velocity. So that is actually appearing here. Okay, so this is the end of the first lecture, where my objective was to give you the brief idea about the finite difference method and the governing equations, and how to set up a problem. Okay, now we will take a 2-minute short break, and after that we will move start the next lecture. Don't you can take don't you need not log out, you stay here. We will start the because the third lecture that we have planned based on our outline is all about introduction to uh, here actually third lecture was about finite volume method, but if I start finite volume today, it may be boring because we have already covered finite difference here. So we will do it tomorrow. So let us take this introduction to ANSYS Fluent with the help of examples in this session. Okay, so stay here. You can take a break for 2-3 minutes. We will join soon and start this this lecture. Okay, so thank you for this one. We will come back soon.
Thank you, sir. Thanks a lot.
Thank you. Okay, so it's 3:50. I let us start at maybe 3:55. Okay, 3 minutes break. Okay.
Okay, sir. No issue.
Okay.
Thank you, sir.
Thank you.
Everyone, you can stay in the meeting or you can leave. We will start again at 3:55 as sir said. Thank you.